Hey everybody in Honors Pre-Calc. Today we're going to be learning lesson 2.7, Nonlinear Inequalities. So let's break down that term for a second. Nonlinear meaning not a line, right? So this is going to be expressions that are not in the form y equals mx plus b, or it'll be different than just an x term and a constant term, like it won't be something x plus something. Specifically, we're going to be looking at polynomials and rational functions today. So polynomial, remember, is our series of x terms that are added or subtracted with different exponents, and rational meaning those polynomials, but in a fraction, with a polynomial on top and a polynomial on the bottom. And those are two things that you should already know, as you can see over here in the top right box. You also need to know what an inequality is, and that's the second part of this term for this lesson. An inequality, remember, instead of an equal sign, we have a less than, or a greater than, or less than or equal to, or a greater than equal to. So down here in what you'll be able to do, here's an example of the type of inequality that we'll be able to solve by the end of this lesson. And your answer is not just going to be x equals a number. It's going to be a series of numbers that make the statement true. And you might write the answer as like x is anything less than 3. So you might write x is less than 3, or you might write it in interval notation, the series of results. And that's more what we're going to be doing, is writing the answers in interval notation. So you will be able to graph polynomial and rational inequalities and solve polynomial and rational inequalities today. And the essential question is, how do you graph and solve nonlinear inequalities? All right, so here are our 2.7 notes on nonlinear inequalities. You can see all of these examples are not linear and they are inequalities. So we'll be solving each of those. And so for polynomial inequalities and rational inequalities, we have some new vocabulary, and we have these things called either key numbers or critical numbers. Those terms are somewhat interchangeable, and you're never going to need to know, what is a key number versus what is a critical number. The more common term, especially when you get to calculus, is going to be the idea of a critical number, which is a 0 or an undefined value in an inequality. So that's going to be important for us. So we're going to check for the zeros of the numerator and the zeros of the denominator. And then we're going to create or construct these test intervals based off of those numbers. And you'll see what I mean. So let's try example 1. Lucky for us, the steps are laid out for us. So we're going to set one side of the inequality to 0. In part A, this is already done. So the right side's already 0. Step 2, find the real zeros of the remaining polynomial graphically or algebraically. So to find the zeros, once this is set up with a 0 on one side, we are going to just temporarily solve for the zeros or the x-intercepts. So to do that, we're going to, just for a moment, set it equal to 0. And if we factor this, we'll get x plus 2 and x minus 3. And so our two key numbers or critical numbers here are -2 and 3, okay? So the next thing that we're going to do is figure out the intervals of our solution based off of what we're going to call a sign chart. But before we get to that, let's just look at the graph so you can kind of tell what is going on here. So if I just graph, y equals x squared minus x minus 6, this original function, not a graphic. Well, it might help if I set my viewing window to normal. So I press zoom 6 to get this back to normal. Now normally, if this was equal to 0, the answer would just be -2 and 3, right? X equals -2, x equals 3, we'd be done right now. But we want to know, when does this expression equal something that's less than 0? So the answers aren't -2 and 3. In fact, -2 and 3 aren't answers at all, because they make this statement equal 0, and that's not less than 0. So if you think about the graph, what we're actually trying to find is all of the x values where the curve is below the x-axis, because anything below the x-axis has a y value less than 0, right? So we can already tell based off this graph that our final answer is going to be between -2 and 3. That's when our curve's below the x-axis. But we're going to do this algebraically. And algebraically, we do something called a sign chart. And a sign chart is really important when you get to calculus. So this is going to be a good preview for us. So we draw, basically a number line, and we're only going to put 2 numbers on it, and that's going to be our critical numbers, -2 and 3. And so now what we're going to do is we're going to test each of these intervals that are separated by these bounds, because those are all potential solutions. So think about like this part of the number line over here represents -∞ to -2. This part of the number line right here represents all the numbers from -2 to 3. And this part over here represents all the numbers from 3 to infinity. And what we're saying is that each of these 3 intervals behaves the same way within its interval. Everything from -∞ to -2 is either going to be all positive or all negative values for the original function. So we're kind of focused on this here. Everything between -2 and 3, when we plug that number in for x, it's either going to give us all a positive answer or all a negative answer. And anything from 3 to infinity is either going to give us a positive answer or a negative answer. So for example, if I plug in 0, that's a number between -2 and 3. If I plug in 0 for x, I'm going to get 0 minus 0, so 0 minus 6, so negative. So I got a negative answer. Any number between -2 and 3 that I plug in here, that means that all of those numbers are going to give me a negative answer. And we can test it if we plug in 1. We get 1 minus 1 is 0, minus 6 is -6, okay? It still gave me a negative number. So I put a little negative sign up here to represent that everything from -2 to 3 is negative. If we go from -∞ to -2, and we have to pick a number to plug in, let's pick a convenient number. Let's try -3. So I'm going to write it out down here so you can see what I'm doing. I'm just going to test -3. So I got 12 minus 6, which is 6. So that's positive. So this is going to be positive. Any number from -∞ to -2 is going to be positive. And let's try something from 3 to infinity. So the easiest number to plug in is going to be 4. Again, I'm plugging that 4 in directly into the original expression. And so we get 16 minus 4 minus 6. 16 minus 4 is 12, minus 6 is 6. So that is a positive number. So everything from 3 to infinity is going to be positive. Notice these are parentheses, so we're not including the 3 and we're not including the -2 in our sign chart. We already figured out from over here, remember, that the -2 and 3 make this equal 0, so that does not count. But there's our sign chart. So we completed the sign chart. So remember, we are interested in that expression being less than 0. So based on our sign chart, we know that from -2 to 3 is when we're less than 0. So our final answer, we're going to write in interval notation from -2 to 3. And that's not an ordered pair. That's the portion of the domain or the portion of the x values that make this inequality true. And we already knew that based off the graph, right? So if you're solving this in a graphing way instead of a algebraic way, you can see that our graph matches our sign chart from -2 to 3. We were below the x-axis, so it was negative. Anything less than -2 had a positive y value. Anything greater than 3 had a positive y value. All right, so we're going to try this again, but for the next few, we're only going to solve algebraically. You can check on the graph, but I think we made that connection, right? So let's keep going. So let's just make sure we're following these steps here. So for letter B, first step, set one side of the inequality to 0. So I'm going to add 48 to the other side, and we'll end up with 2x cubed minus 3x squared minus 32x plus 48 is greater than 0. Okay, so now we need to find the zeros. And I do not know off the top of my head what those would be, right? None of our factoring methods are going to help us with this. So, you know, I said we're not going to use a calculator, but we're not going to get the answer with the calculator, but I think we're going to need to use the calculator to get the zeros. So let's do that. So I'm going to type this in here and graph. And we're looking for the zeros. Okay, it looks like there's one at -4, something between 1 and 2, and at 4. So let me just check the table. Yep, there's -4 and there's 4. Those are both at 0. So we have x equals -4. There was something in the middle, and then there was a 4. So I'm going to go to calc to 0. So I press second trace 0, and I'm going to go a little bit to the left and a little bit to the right of that missing x-intercept so we can figure out what it is. And look, it has an x value of 1.5. So there's our 3 zeros. So now we're going to construct our sign chart. And this time we're going to have 3 points on it, and we're going to make sure they're in numerical order, in ascending order. So it's going to go -4, 1.5, and 4. And now we have to check a number that's within each of these 4 intervals, right? We just kind of took that whole number line, think of it like a loaf of bread, and we sliced it 3 times. So now there's 4 pieces. So we have to pick one number from each. So I always want to use 0 if it's available, because that's really easy to plug in. So I'm going to plug in 0 for this interval. And now I'm just going to try to plug in the number that's closest to 0, but is still like an integer, like a positive or negative whole number. So between 1.5 and 4, I'm going to plug in 2. Between 4 and infinity, I'm going to plug in 5. And remember, we can't plug in 4 because that's on the endpoint of the interval. And then something below -4, so I'm going to pick -5. So I'm going to try each of these 4 numbers and see how it goes. Okay, so I'm going back to the calculator again, and I'm just going to type each one of these in. I already did this ahead of time, so I'm going to just tell you what the answers are. So for -5, and we're going to plug it in after we already had it equal to 0. So we're plugging it into this. And let's see. So -infinity to -4, I'm going to plug in -5, and I get -117. That's negative. If I plug in 0, I get 48. So that's positive. So anything between -4 and 1.5 is going to be positive. If I plug in 2, I get -12. That's negative. If I plug in 5, I get 63. And that's positive. Okay? So we wanted to be greater than 0. So we are interested specifically in the positive intervals. So our final answer is going to be from -4 to 1.5, union from 4 to infinity. That's the 2 intervals that have positive y values. All right, let's try one more. Letter C. So first step, move the 6 to the other side. There is something different about this one, so we're going to have to do a little bit of extra work, and I'll show you why. So for this left side, again, can we factor that? I feel like we can. I don't have this written down, so this is going to be a good test here. So we have 4x and x. Can I make the middle equal 5? -2 plus 3. So we have 4x squared minus 8 plus 3 is -5 and -6. Yeah, that works. Okay. So that was kind of nice. So if we wanted to find the zeros, the first one would be subtract 3 and then divide by 4. So it'd be -3/4. And the second one would be x equals +2. And so we're going to set up our number line here. This time we only have 2 slices, -3/4 and +2. And we're going to check each one of the intervals. So let's see what we got. If we plug in, I would plug in 0 here, 3 over here, and probably just -1 over here because that's still lower than -3/4. So if we plug in 0, we'll get 3 times -2, so that's negative. When we plug in 3, we'll get a positive times a positive number, so that's positive. We plug in -1, we'll get -4 plus 3, so a negative number and a 1, -1 minus 2, a negative number. Negative times a negative is a positive. And the trick here is now to realize that this is greater than or equal to. So when it's greater than or equal to, we actually have to check the endpoints. So let's make this note down here. For greater than or equal to and less than or equal to, check endpoints of intervals. We could also call those the critical numbers, right? Okay, so we have to check the -3/4 and check the 2. In this question, and in the questions on the next page, when we get to the rational inequalities, we're going to actually want to plug into the original instead of plugging into the updated one. So let's practice that now. So we're going to plug in -3/4 all the way back up here. So I'm on my calculator now. I'm going to type in here -3/4 for x. So 4 times -3/4 squared minus 5 times -3/4. And that made that statement true. So I'm going to put, what should I put here? A little check mark to show that that worked. And I'm going to try the same thing with 2. And it equals 6 again, and that's what we wanted. So that makes it true. So I'm going to put another little check mark to show that that was true. So if I had plugged in 2 and it wasn't true, I probably would have put an X to show that it shouldn't be included. But both of these should be included, and we're specifically interested when we're greater than or equal to 0, so we're looking at the positive answers. So for this one, we're going to have -infinity to -3/4 and a bracket, because we're including the -3/4, union, bracket 2 to infinity. Remember, infinity always has parentheses. These numbers have brackets because we're including the 2 and the -3/4. So there's our intervals here. Remember, what this is telling us is that all of these numbers make this inequality true. All right, so that is how we do polynomial inequalities. Remember, for the first 2, we just had less than or greater than, so we didn't really care about the endpoints of the intervals. For letter C, if it's greater than or equal to, now we have to check the endpoints to see if they're included. Let's flip over to the back. Example 2, rational inequalities. This time we have 4 steps. Step 1, set one side of the inequality to 0. So that step is the same as we had for the polynomials. Step 2, use common denominators to create one rational function. Actually, both of these, oh, you know what? They don't have common denominators yet. We'll see that in a second because the other side isn't 0 yet. So let's start with that. We'll get to the other steps as we get to them. So for letter A, first thing we're going to do is subtract 3 to the other side. So we have 2x minus 7 over x minus 5 minus 3 is less than or equal to 0. I wrote a 3 for some reason, but that should be a 0. Okay. So now we have to find a common denominators so that we only have one fraction over here. It can't be a fraction and a number. It should just be a fraction. So what I'm going to do is I'm going to make this 2x minus 7 over x minus 5 minus 3 times x minus 5 over x minus 5. Right? Because if I multiply the 3 by x minus 5 or x minus 5, that's not changing the value of the 3. I multiplied by something divided by itself. So it's still technically equals 3, but we're just manipulating what it looks like so that we can combine here. So the next step is going to be to combine. So we have 2x minus 7 minus 3 times x minus 5 all over x minus 5. Right? So when you combine with common denominators, the bottom stays the same. So that is less than or equal to 0 still. And I'm going to keep going up here. So let's actually distribute the negative 3. So we have 2x minus 7 minus 3x plus 15 all over x minus 5. And combining like terms, I get 2x minus 3x is negative x, and negative 7 plus 15 is positive 8 over x minus 5. All right, so we did it. We did step 2. So now we have one rational function. Step 3, find the real zeros of the numerator and the denominator graphically or algebraically. All right, so for this step, we have to individually find the zeros of the numerator and the denominator. So we're going to set the numerator equal to 0. And we're going to set the denominator equal to 0. And that's going to be our 2 critical numbers. So yes, they mean different things, right? The 8 came from the numerator and the 5 came from the denominator. But they both kind of chop the number line into intervals that we're interested in. So we're going to make our sign chart again. And we're going to use positive 5 and positive 8. And for rational inequalities, we're always going to go back and check the original function because things might have switched around when we manipulated it. So for rational inequalities, always check original inequality for the sign chart. Okay. So technically it's called a sign chart because we write a plus or a minus. Whoa, I bumped the camera. Technically it's called a sign chart because we write a plus or a minus, but we are not going to be able to do that here because we're not just interested if the interval is positive or negative. We're going to be interested if it's less than or equal to 3. But that's okay. We'll still make it work. So first we have to pick a number in each of these intervals to check. So I always look for 0 if possible. So I'm going to check 0. I'm going to check 6, and I'm going to check 9. So let's plug each one of those in. So if I plug in 0, I'm going to get negative 7 over negative 5. So that's 7/5. And is that less than or equal to 3? Yes, it is. So I'm going to put a check there for that interval. Notice that since this is less than or equal to, we have to check the endpoints. So let's do that. So we have to check the 5. So for 5, what do we got? We got 10 minus 7 is 3 over 5 minus 5. That. So 5 made this inequality, this fraction, divide by 0. A number that's dividing by 0 doesn't exist. So it can't be less than or equal to 3 if it's not even a number. So we definitely do not want to include the 5. So I'm going to put an X there. Next, we have to check a number between 5 and 8. So let's check 6. And if you check 6, you will find that the number does not make this inequality true. The number 8 does make the inequality true. And the number 9 does make the inequality true. So we made check marks or X's for each interval and each endpoint. And now it's time to construct our actual interval in interval notation. So we definitely want to include this interval over here from negative infinity to 5. The 5 did not work, so we're going to use a parenthesis. And then we're going to do U for union. And we include the 8 and go to infinity. Okay? There you go. All right, last one, letter B. Let's try those steps again. So the first thing we're going to do is subtract 4 to the other side. That should be a minus. Minus 4 is greater than 0. I'm going to make a common denominator. So then we have 5x plus 12 minus 4 times x plus 2 all over x plus 2. So we have 5x plus 12 minus 4x minus 8 all over x plus 2. And 5x minus 4x is x. 12 minus 8 is positive 4 over x plus 2. And so our critical number from the top is going to be negative 4, and from the bottom is going to be negative 2. So now I'm going to make my sign chart. And so we're going to check one number from each interval. 0 is over here this time, so I'm going to check 0, I'm going to check negative 3, and I'm going to check negative 5. Again, I just picked those numbers based off of what's closest to 0 and won't be too hard to plug in. But you can pick any number between the interval and it'll still work. You don't have to pick these numbers that I'm picking, but let's check 0. So if you plug in 0, you're going to get 12 over 2, which is 6. 6 is greater than 4, so it worked. If you plug in negative 3, you're going to find that it does not work. And if you plug in negative 5, you'll find that it does work. Hey, good news. This question is greater than. It is not greater than or equal to, so we don't have to check the endpoints. If you want, you can even just cross them off because we know that they're going to not make this true. Okay? So last thing we have to do is write our interval. So it's going to be from negative infinity to negative 4, and from negative 2 to infinity. All right? So a couple last things here. That was the last example. Note that for the polynomials, when we did not have fractions, it was okay to make a sign chart based off of the final equation that we had set equal to 0. As soon as we got to rational inequalities, we instead had to make checks and x's based off of the original inequality, because some of our critical numbers are coming from the numerator and some from the denominator. You can see from right from this first one that sometimes it makes it true and sometimes it doesn't. So we can't, we have to check everything based off of the original, not just based off of the final answer, okay? And if you look at the worksheet, let's see, is there anything I want to point out here? You know, this is pretty standard, it's pretty much straightforward, same as the examples in the notes. I would say that in number 3, notice that it's already factored for you, so you don't have to do very much. It's already factored. You can just set that equal to 0. And in number 7, you're going to have to do a little bit of work to find the common denominator, because by the time you add the 1 over here, now you have 3 different terms. So I'll tell you right now, your common denominator is going to be x minus 1, x plus 1. So you only have to multiply through to each of these fractions, either the 3 over x minus 1, the 2x over x plus 1, or the 1. You have to multiply something on the top and the bottom that's missing in order to end up with this common denominator. So for the first fraction, remember, you only have to multiply by x plus 1 over x plus 1. In the second one, only multiply what's missing. And in the third one, you're going to have to multiply everything on the top and the bottom. So make sure you do that. And everything else should be pretty good. All right. So that's the end of 2.7. Thank you so much for watching. And as always, let me know if you have any questions.